So yesterday we ended with a proof that 3-SAT is NP-complete, right? And that proof involved, we assumed that SAT is NP-complete. So this is it's a theorem, but we didn't prove it. Oh yeah, go ahead. And so to prove that 3-SAT is NP-complete, we reduced SAT to 3-SAT. Now I understand that we kind of were running out of time at the end, so I did write down the proof, but I didn't really explain all the details. So I wanted to just kind of go over this kind of briefly again, and actually I just want to explain the details in one particular example, and then hopefully you can see how that generalizes to all Boolean expressions. But just to recap what we were dealing with, so you want to basically transform the SAT problem into 3-SAT, right? So you're given a SAT problem, so you have a Boolean expression, and you might remember we can assume that it's in conjunctive normal form. Okay, conjunctive normal form, remember that's just like you have these clauses. So each clause is a big OR thing with a bunch of literals, which are variables or their negation, and between them you have AND. So for example, this is in conjunctive normal form, where so each of these things, these are the clauses, right? So a clause, remember, it's just a bunch of either variables or their negation separated by OR. And conjunctive normal form, you have a bunch of clauses separated by ANDs. And so each of these things, like a variable or its negation, remember we call these literals. So this is an example of, this is an expression in, and I'm not going to write conjunctive normal form every time. So CNF means conjunctive normal form. It's a really long thing to say, unfortunately. So you're given a general one of these, and you want to transform it into an instance of 3-SAT. And 3-SAT is, so 3-SAT, for 3-SAT, the instance is a Boolean expression in conjunctive normal form, but where all of the clauses only involve at most 3 literals, right? So this is not an instance of 3-SAT because here you have 5 literals in one clause. We want to get that down to 3, right? And the proof that I told you, but I didn't explain the details, is basically you go through your expression, you look at every clause that has more than 3 literals. So this is a general kind of form of a clause, so that could be Z1 up to ZK, where each ZI is a literal. And you just replace that by 2 clauses where you take Z1 up to ZK minus 2, or U and not U, or ZK minus 1, ZK minus 2, where U is it's a brand new variable. And something I didn't make clear, and yesterday, is that this U, so you have a new variable for every such clause. So it's not just a single variable that you put in all the clauses, but it's a new one for every clause. So hopefully I can make that clear in this example. So here what you would do is you replace, so you take this first clause, you replace it by two clauses which look like, so here it has 5 things in it. So K is kind of equal to 5 here, right? I take the first K minus 2 things, so I write them again. So Z1 or not Z2 or Z3. And then I put an OR. I make a new variable. I'm going to call it U1 because there's going to be several new variables. Well, there's going to be 2 new variables. And then I have a second clause where I just take not U1, and then I do OR, and I take the last 2 elements. So that's, here I'm writing this clause. So X4 or not X5, okay? So this, these 2 clauses now correspond to the first clause here. And then I do the same thing here. I take not X1 or X2, or now I need a new variable, so it's going to be different than this variable. I call it U2, and then I take and not U2 or X4 or X5. Yeah. Good, thanks. It's hard to, not make mistakes when you're standing. The closer you are to the board, I think it turns out it doesn't matter. I mean, I could add, you mean like maybe put brackets here or something, and maybe put brackets here. This is perfectly acceptable as well. It turns out just because of how this AND operation works, it doesn't turn out to matter. Kind of if I take kind of X and Y and Z, it turns out it's exactly the same. You know, if you think of all the ways you can assign these variables to truth values, it's exactly the same as any other way of bracketing it. So both of these are true if and only if all three of them are true. So so maybe if you want to be really technical, maybe you should put more brackets than I've put. But it turns out it doesn't really matter, so you usually just omit those brackets in this case. But when you have something like this, which hopefully I haven't written, if you have something like this, this doesn't really make sense. Here you would need some brackets. But when you have a bunch of ands or a bunch of ors, you don't really need brackets. That makes okay. But yeah, so right. So now I claim. So okay. So this, by the way, I haven't gotten to instance for 3-sat yet, right? Because I still have a clause of size 4. Okay. But you would just then repeat this. So repeat. So in the proof we repeat until all clauses have at most 3 literals, which will certainly happen because here we replaced a clause of length k with a clause of length k minus 1 and one of length 3. So in particular, every time you do this, the maximum size of a clause is going to go down by 1. So eventually it'll get to at most 3. Okay, now I need to kind of argue that these things are equivalent, right? So I want to say, so suppose I call this one, I don't know, star, and I call this one a double star, right? I want to say that star is satisfiable. So star is satisfiable. Satisfiable meaning there's a choice of the variables that outputs 1, if and only if double star is. Okay, in this, I mean, if you look at one particular example, it's kind of a weird thing to say, right? But we should be thinking of this in general, right? Because, okay, either this is going to be satisfiable or not. There's no, okay, so for this direction, right? So suppose that this one's satisfiable, right? So there's a way of choosing the variables x1 up to x5 and u1 and u2 such that this outputs true. Well, I claim that if I just set the same values of the variables here, then it's going to be true. And the reason for this is that, so for the proof of this, well, if I look at u1 and not u1, these can't both be true, of course, because they're the negation of each other. So if I look at this kind of this or thing, right? If this one's false, then one of these has to be true. And that would force this whole clause to become true, right? And on the other hand, if this one's false, then one of these is true, and so one of these is true, and that forces this, that makes this true, right? So therefore, like x1 or not x2 or x3 must be true, or the other bit, so x4 or not x5. So one of these things is true, but that gives that the first clause is true. And then the exact same thing happens for this second clause. So these things can't both be true, so therefore this second clause must be right. And the other direction is, well, similar, right? So if I can assign these variables to be so that so star outputs true, then either so the important thing here is that u1 only appears in these two clauses. It doesn't appear anywhere else, right? So suppose I have set the variables so that this clause is true, then certainly either this, so x1 or not x2 or x3 is true, because either there's a true thing in this part or there's a true thing, one of these two things must be true, or both. So if both happen, then then this is going to be true already. But so suppose these two are both false, I would just set u1 to be false, this will be true, and I know that one of these would have to be true, because, so it's kind of confusing, but hopefully it's, Is that clear? So I'm just going to say the other direction follows from the fact that u1 and not u1 only appear in two clauses of double star, and that turns out to be the kind of important thing. You can always set them, whatever happened, you can always set them to make these two things true, so long as this statement is true. I know, I feel like I'm just saying true. It's kind of confusing, but yeah. Hopefully this example, if you go back to this, in the if you want to understand this proof better, perhaps going back to this example can help. Okay. Any questions? Okay. So let's now move on to something hopefully you'll find slightly more interesting than this Boolean satisfiability problem. So we're going to take the fact that 3-sat is NP-complete, and we're going to prove that a bunch of different problems on graphs are NP-complete. So first, including some problems we've already seen, we've already sort of discussed earlier in the module. Okay, so first I need a definition. So given a graph G, a set a subset of the vertices is called a clique, or perhaps some people, I think some people pronounce this word clique, but I'm going to pronounce it clique. If UV is an edge for all pairs UV and S, which are distinct. So all I'm saying is it's a set of vertices which includes all the possible edges within that set. So it's a set of vertices like, you know, so a clique of size 5 would just be 5 vertices, and all the possible pairs of vertices in that set are joined with an edge. This word clique, right, it has a meaning in English, right? It's like, if you think of some sort of social network, it's like, I don't know, it's a bunch of people who all know each other, or they're all friends, right? If you think of two vertices as being adjacent or joined with an edge, if they're friends, then this is a sort of clique in the graph. So, okay. Is that definition okay? Okay, so okay, so the following problem is called clique in all caps. I don't know, when people, for some reason in computational complexity, when people define problems, they like to put everything in all caps. I don't know why, but yeah, if you see this written somewhere, it's not like, you shouldn't take it as I'm shouting at you or something, you know, clique, but yeah, it's a decision problem. So, okay, so the input, you have a graph G, and an integer k, positive integer. And the question is, does G have a clique of cardinality k? So does it have k vertices that are all joined to each other in the graph? And there's one subtle thing that I want to point out here. So I'm not sure whether this comment, but this comment could be helpful to you, you know, to not get confused. So it's very important. Well, yeah, it's important that k is part of the input. Okay, and it's not just some sort of fixed parameter of the problem, right? So, because if you wanted to have a polynomial time algorithm for this, for example, it would have to be polynomial not just in the graph G, but also polynomial in K. And that's what makes this difficult. So you know, if you had a polynomial time algorithm, and as we're going to see in a second, it's very, very unlikely that you have a polynomial time algorithm, but it would have to be polynomial in G and in K. So for example, if I just say, okay, I'm going to check all the sets of size K and check if they're cliques, well, that takes V choose K steps, which is sort of V to the power K, which looks polynomial with respect to the graph, right? It's just V, it's just the number of vertices raised to power K, but that's exponential with respect to K, right? So anyway, so what we're going to prove now is that clique is NP-complete. Okay, so as usual, in all of these NP-completeness proofs, you have to remember that there's two parts to it, right? You have to show that the problem is in NP, and you have to show that it's NP hard, right? So it's very easy to forget one of these parts, which is showing that it's an NP, right? Because this is usually a very easy thing to do. So well, yeah, can anyone tell me why clique is an NP? Yeah. Yeah, exactly. So yeah, just to repeat that. So if you, yeah, basically because, you know, a clique of size K is itself a certificate, right? So that's a certificate for a yes instance, and as was said, you can check that this is a valid certificate in polynomial time because you just have to check every pair of vertices in the clique, and so it can be checked. You can check that it's a valid certificate in, yeah, I'll just write order, yeah, so you just have to check kind of k choose 2, you have to check every pair and see that it's an edge. That's k choose 2 steps. That's order k squared steps, which is polynomial in the size of the input because our input, involves g and k. So now we want to show that it's NP hard. So for NP hardness, so now we're going to reduce 3-sat to clique. Then we're going to know, and then if we do that, we'll know that it's NP hard. So remember how reductions work, right? We need to take an instance of 3-sat and transform it somehow into the clique problem. And the transformation has to be such that, the 3-sat thing is satisfiable if and only if the graph has a clique of size at least, or a clique of size k. Okay, so take any instance of 3-sat. So it looks like, so it's C1 and C2, like CK, where each of these are clauses. Right? And so it's a clause involving at most 3 literals. Right? It's an instance of 3-sat. And from this we want to build a graph. So notationally this is a bit annoying. So I need to define a bunch of notation here. So okay, so let Li, so for I between 1 and k, let Li, essentially this is going to be the kind of length of the ith clause, which, okay, we could think of them as all being basically, I mean, each of them has at most k, or most 3 literals. Annoyingly, that, they could have size 3, they could have size 2, or size 1, right? So this is the number of literals in clause I, and we write clause I as so Z1I or, and now, okay, I'm going to write dot, dot, dot up to Z Li I. This is a really weird, I mean, we know that all of these things only have 3 literals or less, but I don't know how many they have exactly. That's the annoying part. But basically, I mean, if Ci looks like, let's say, I don't know, x2 or x3 or not x10, right? Then Z1I, so this is an example, would just be x2, Z2I is x3, Z3I would be not x10. Right, so this is, so you just look at the literals that appear here and label them like this. Yeah. This one, so actually no, I mean, here I actually mean, so you have actually k, which, in this one, right? So you have, yeah, it's kind of confusing sometimes to keep these things straight, but you have, so each clause itself involves 3 literals at most, but there are k clauses. So here I'm going over all the clauses, and Li is the kind of length of the ith clause. Yeah, thanks. It's good to clarify these things. Okay, maybe I'll start here. Okay, so continuing on this proof. So all I've done is get some notation, right? So now we let G be a graph. So E be the graph where the vertex set is just going to be the union from I is 1 up to k of Zi j, where j ranges between 1 and the length of the ith clause. Okay? And we think of these things as being all distinct, right? Because, so you know that, like for example, there could be many clauses that involve the variable x1, for example, right? But for all of those clauses, we make a separate vertex for x1. So so the number of vertices here, like, is going to be exactly equal to the sum of I from 1 to k of the length of the ith clause. So we don't kind of, even if two of these vertices correspond to the same literal, we treat them as separate vertices, not the same vertex. Clear? And okay, so now so the edge set is defined so that if I take two vertices, it makes an edge if and only if, so this is ij, this is z I prime j prime. So this makes an edge if and only if, so two things have to be satisfied. So I has to be not equal to I prime, and zji and zj prime I prime are not just negations of each other. So I'm saying it's not the case that, if this is equal to some variable x, we're saying that this one is not the negation of x. So in other words, we're saying that these things could, in theory, be true at the same time, right? Or false at the same time. So is it clear how this graph is constructed? I mean, it's kind of notationally awkward, but I think this definition perhaps is not, it's not a complicated thing. If you were given the formula or the expression, the Boolean expression, you could draw this graph pretty easily. It's just the notation is kind of, it's kind of awkward. But and one thing that should be clear is that the amount of time it takes you to make this graph is not very long, right? So it's just a polynomial in the length of the original expression. So this is indeed going to be a polynomial reduction. But okay, so what we claim is that G has a clique of cardinality k if and only if, well, the original SAT formula, so C1, or SAT Boolean expression, C1 and C2, etc., up to CK, is satisfiable. So basically I'm claiming now that by doing this transformation, we've exactly transformed this 3-SAT problem exactly into the clique problem, right? And therefore, the clique problem must be hard. Okay, so one direction, suppose that C1, well, suppose that the expression is satisfiable. Well, so then every single, so remember this is a bunch of and things, right? So every single one of these C1 up to CK must have some literal that's true. So for I from 1 to k, there exists some j depending on I, such that zi, ji is true. Okay, so I'm assuming, so I'm saying it's satisfiable, so I'm assuming we're looking at some assignment of the variables that makes it true. And so since this whole expression is true, every single one of these clauses must include some variable that's true, or some literal that's true. And now I just let S be the set of these literals. And this is a subset of the vertex set of the graph, right? Because remember, these literals correspond to vertices in the graph. And I claim it's a clique. So, well, I mean, it's not too hard to see it's a clique because, well, you just have to check the conditions of having an edge. So if you take two different vertices from this, from S, they correspond to different values of I, let's say I and I prime. Okay, so they satisfy the first condition of being an edge. And there's no way that one of these could be the negation of another, because I'm assuming that every single one of these things is evaluated to true, so you certainly cannot have one being the negation of another, because those could never be true at the same time. So S is a clique, essentially by definition of the edge set. So if you just go through those two conditions, you'll see that they're both, if you take any pair in this set, both conditions are satisfied. okay? Because these things are true. So by definition of E, and this fact that all of them are true, and it has size k because, well, it just has size k, right? So because for every I, we were able to pick some ji. So the size is k, so therefore G has a clique of size k. Yeah. Oh, it does. So a clique of size 1 is, yeah, a single vertex is a clique. So if you look at the definition, it says for every pair of distinct vertices, they're adjacent, or they have an edge between them. That would hold vacuously when k is 1, because there simply wouldn't. Yeah, it's kind of a confusing set theory thing. But if I have a set of size 1 and I make a statement about any two distinct elements of it, any such statement is true because there aren't two distinct elements of it. A clique can be of it can be of cardinality 0 as well. The empty set is a clique. Yeah. So maybe I'll make a note here. So if the set is size 1, then S is a clique. And well, even if it has size 0. But that's just a sort of annoying logic thing that if you make a statement about any two distinct things and there aren't two distinct things, then that statement is always true. So yeah, let's not worry about these kind of semantics. But that's a good question. Thanks. Okay, so what we've proved so far is that if this formula is satisfied, basically just by taking the true literal from each clause, I would find a clique. And now we have to go the other direction and assume that there's a clique and prove that the formula is satisfiable, or the Boolean expression is satisfiable. So now suppose G has a clique S of size k. Well, so one thing I know is that if I have two vertices, so if I have two vertices in S, if I have distinct vertices in S, let's say distinct, well, remember our definition of an edge, right? So the edge, if these two things are in S, they're joined with an edge because S is a clique, and so I must be different than I prime, right? And Zji and Zj prime I prime are not negations of each other. That's the definition of the fact that they're adjacent. And so basically, if you look at each of these literals, okay, so some variable, so each of these is either equal to a variable or the negation of a variable, and you never have one which is equal to a variable and one equal to the negation of the same variable. So basically, each variable appears in S well, it can appear many times as long as it's always either just the variable or the negation. Okay, you can't have both. So basically, if we can set the variables so that each element of S is true, and this will not create any conflicts. So by conflict, I mean, so conflict would be like saying, I have to set this variable to true and false at the same time, right? So, i.e., no variable is set to true and, well, when I say true, of course, I mean 1 and 0. True and false is, yeah, true is 1, false is 0. And, okay, there's some variables that might not appear at all here, but we just set, it doesn't really matter what we do with those. So any other variables get set to 0. And this is going to be a satisfying assignment because, okay, actually, there's one thing I haven't really said here. So by pigeonhole, each clause, because so any two different vertices in S have different values of I, right? They come from different clauses, and there's only k clauses. So each clause includes exactly one literal in S, right? And so by setting each element of S to be true, I'm going to make all of the clauses true, and that means the expression is going to evaluate to true. So the expression C1 and C2, etc., up to CK evaluates to true or 1 or whatever. Okay, any question? Yeah, all of this stuff is kind of abstract. The notation in this proof is kind of annoying. I mean, I couldn't think of any better way of doing it. But in practice, you could, yeah, it's not too hard. You know, if you go through this proof, hopefully, it's not too hard to see. Each individual step, I don't think, is very hard. But okay. So this is the first kind of graph theory type problem that we've seen as NP-complete. Now I'm going to tell you that basically for free, you know, for no other kind of, for completely for free, we get a bunch of other problems being NP-complete, okay? Because they're really, really, really equivalent problems. So another definition, so I define clique, that's a set of vertices where all of them are joined by edges. Now you can kind of talk about the opposite. So a set of vertices is a stable set, although some people call it an independent set, some people call it a stable set. I mean, I think the graph theory world is split about half-half. So you might see the word independent set some places. If UV is not an edge for all distinct vertices in V, or in S. So again, so this is kind of a weird thing, right? But a single vertex is going to be a stable set, because it is true that if I pick two distinct vertices in a single element set, they're not adjacent, but that's just because you can't pick two distinct vertices. So a single vertex is a stable set, the empty set is a stable set, and if you take a set of vertices and you don't put any edges, that's going to be a stable set. So it's kind of clear that it's going to be it is NP-complete to decide if a graph has a stable set of size k, right? And why? Well, I mean, basically a stable set's the opposite of a clique, right? Clique has all of the edges, a stable set has no edges, and so the proof is basically just consider the graph. So this is called the complement of G, which is the graph G bar, which has the same vertex set and UV. So a pair of distinct vertices is an edge of the complement if and only if UV is not an edge of G. You just go through all the pairs. If it's an edge of G, you take that edge out. If it wasn't an edge, you put an edge in. And you can see that finding a stable set in G, or a clique in G, is the same as a stable set in G complement. So these problems are the same, right? And one more problem, which kind of connects back to what we were talking about in week 3, is the vertex cover problem. So remember, a vertex cover is a set of vertices that hits all the edges, and it's also NP-complete to decide if, let's say, G has a vertex cover of size at most k. Why is that? Well, so that is because if I take a set S, okay, so actually, no, I'll say, so a subset S of the vertex set is a stable set if and only if V minus S, so the complement of S and V, is a vertex cover. Because, so this is not hard to argue, right? Because, so if V is a vertex cover, it hits all the edges. Therefore, the complement of, so if this set is a vertex cover, it hits all the edges, so its complement can't contain an edge. Because if it did, that would be an edge that doesn't get hit, right? And vice versa, if there's no edges here, then the complement of that set must hit all the edges. And so, yeah. So this turns out to be NP-complete as well. which is sort of weird because, remember, so if G is, if the input graph G is a bipartite graph, so then the problem's in P. So then the problem's in P because we know how to find the biggest matching in such a graph in polynomial time and by Koenig's theorem. So this is applying Koenig's theorem and max matching algorithm. So you could just find the biggest matching, apply Koenig's theorem, max matching size equals minimum vertex cover, and you'd be done, right? You just see if that's bigger or less than k. Okay, so I think that's all. So yeah, see you next week.